So for this video, we are looking at exponential growth. So imagine you have some rate of change of y with respect to time, and it is proportional to y itself. So this is actually exponential, but you wouldn't know it in this form until you've actually done some problems. But what we have here is a y to the first. So if I was just told to solve this differential equation without knowing anything else, my very first step would be to separate the variables. So I'm going to take my dt and move it to the right, and I'm going to take my y to the first and move it to the left. So I would actually divide by this y to the first. So what I have here is a 1 over y dy equals k dt. So looking at that, I would integrate both sides, and this 1 over y is logarithmic. Now, just a reminder that if you try to do it the power rule, you have a y to the negative 1. If you try to add 1, negative 1 plus 1 is 0, then divide by 0, it doesn't work. That's your clue to remember, hey, this is logarithmic. So this is the natural log of the absolute value of y on the left-hand side. On the right-hand side, we're taking the antiderivative with respect to t, so kt plus a c. So remember that your goal is always to get to y equals, not to the natural log of the absolute value of y. So what we have to do is get rid of the natural log, then get rid of the absolute value, and then we'll be focused in on the y itself. So to get rid of the natural log, what I'm going to do is actually change forms. This is the logarithmic form of the equation. I know ln is base e, so I'm going to change forms. It will be e to the power of kt plus c equals the absolute value of y. So you can see how this could become exponential really quickly. We now have e to some power. So just a reminder that this is actually equal to e to the kt times e to the c. And the reason I know that is if I have two things multiplied that have the same base, I can add the exponent. So what I'm doing is undoing this plus sign right here and splitting it into two things that are multiplied. Well, at this point, I've gotten rid of the natural log, but I want to get rid of the absolute value. So one thing you can do is say let, and you pick some other letter. I'm going to pick, I don't know, big letter A equal plus or minus e to the c. So what that does is it gets rid of the e to the c. I'm going to put an a here, but the plus or minus lets you take away the absolute value. So I'm going to say the absolute value of y equals a times e to the kt. I'm sorry, there's no absolute value anymore. And we actually have it. So we just have an exponential equation. A would be like your start amount, and then it's raised to the e to the kt. It's exponential. We are done. So it's strictly exponential if you just have some constant here with a y to the first, and that's your clue. If you see a y to the first, you're going to have some exponential solution. Now, in Calculus BC, we can have all different kinds of things multiplied in here. So, just to do a couple of examples, let's say that we knew dy dx equals 6x squared y, and I'm going to give you an initial condition. I'm going to say y of 0 equals 4, and I want you to solve this differential equation. Now I know there will be exponents involved. I'm catching it because I see the y to the first over here, but if you don't just know right away, it's okay, because when you separate variables and start integrating, it will happen. So I'm going to separate variables. I'm going to take the y, move it to the left, so it becomes a 1 over y dy. The dx comes to the right, 6x squared dx. And I'm going to integrate both sides. The left-hand side, again, we have a 1 over y dy. That is the natural log of the absolute value of y, equals, and we're just using the power rule to take the antiderivative, so it will be x cubed. Divide by the 3, and I have 2x cubed plus c. Going through the steps, the next step I'm going to do is get rid of the natural log. So I'm going to change forms. That's base e. So e to the 2x cubed plus c equals the absolute value of y. I'm going to let, and I'm just going to use k. Generally people use k. k equal plus or minus e to the c. And I can rewrite this by saying, all right, then that means y equals k e to the 2x cubed. And remember that this is e to the 2x cubed times e to the c. So putting in the k for e to the c lets me write the coefficient up front, getting it out of the exponent, and I get to get rid of the absolute value. So this is the general solution. I want the particular solution that contains the point 0.04. So I'll plug in. So I have 4 equals k e to the 2 times 0 cubed. Well, 2 times 0 cubed is 0. E to the 0 is 1. So my k equals 4. And that's one of the nice ways to get a problem like this. If you can get the k out, if the initial condition actually has a starting value at 0, everything's beautiful. So 4e to the 2x cubed. That would be that problem. One more of those, and we have dy dx equals 3x to the 5th times y, and I'll do a starting value of y of 0 equals 7. So the steps remain the same. Separate variables. 1 over y dy equals 3x to the 5th dx. We're integrating both sides. From here, I'm going to save a little bit of space. We're going to say the natural log, the absolute value of y, equals, this will be x to the 6, divide by 6 is a 1/2, plus c. I change forms, so e to the 1/2 x to the 6th plus c equals the absolute value of y. Then I'm going to let k equal plus or minus e to the c, and I have y equals k e to the 1/2 x to the 6th. If I actually want to solve for what k is, I can plug this point in, and if I put a 0 up here for the x, this becomes e to the 0. So 7 equals k, and my answer is y equals 7 e to the 1/2 x to the 6th. Now that's not to say that I always have to be given a point where the x value is 0. It's convenient, but it's not reality. It's not what actually happens all the time. So we're going to work another example where you don't start with an actual x of 0 and y equals some number. So let's do that. So for this problem, let's say we have dy dx equals 2x to the 3rd y. Again, it's y the first, so I know it's exponential. But I'm going to say y of 1 equals 3. So my first steps remain the same. I'm going to separate variables. 1 over y dy equals 2x cubed dx. Integrate both sides. Then I have the natural log of the absolute value of y equals, this will be x to the 4th, divide by 4 makes it a 1/2, plus c. I change forms. E to the 1/2 x to the 4th plus c equals the absolute value of y. Now you could actually start plugging in right here, but we're going to say let k equal plus or minus e to the c, and I'm going to say y equals k e to the 1/2 x to the 4th. Next thing I'm going to do is actually plug my point in. So we have 3 equals k e to the 1/2 times 1 to the 4th. Well, 1 to the 4th is 1 times a half is a half, so I know that 3 equals k e to the 1/2. Well, if I'm going to solve for k, I can just divide by e to the 1/2 on both sides, so k equals 3 over e to the 1/2. So from there, my equation becomes y equals 3 divided by e to the 1/2, or you could have the square root of e in the denominator, times e to the 1/2 x to the 4th. So this is done, it's right, it's fine, but I actually can combine these. I have two things with the same base, and I'm actually dividing. I have e to the 1/2 x to the 4th over an e to the 1/2. So I can subtract the exponents. And I'll have y equals 3e to the 1/2 x to the 4th minus 1/2. And that's another way to look at the solution. And that would be how you actually do the antiderivative. Now it's important to note the steps. To receive full credit on problems from me, you have to show your steps. So you have to address every little piece of this. It's not hard, but you do need to show each step.